Good morning, everyone. What an absolute pleasure it is to be here. My name is Ariana Swearman, and this is my co-investigator, Ashley Pfefferkorn. Under the guidance of our teacher facilitator, Professor John Float, we proudly present our investigation on the effects of microgravity on the quantitative measurements of calcite crystals.
Now, within our bodies, there is a system known as the vestibular system. Pretty much, this maintains our balance, our posture, and our spatial awareness. And if we didn't have that, we'd all probably be falling over or just not have good balance, which isn't fun. And one key component of this within our ears is called otoconia, which are tiny crystals made of calcite, which basically help respond to blunt force, gravity, and if they become dislodged or deformed, it may cause symptoms of vertigo, dizziness, and vomiting. Not fun. And in 2021, a study by Richard Boyle and Joseph Arelas had studied mice otoconia being sent up into space to study their otoconia. Pretty much the results that came back from that for the mice otoconia was surface layering, thickening, and mass increase. So we wanted this to be the foundation for our experiment. However, mice just cannot be sent into space, and for ours, with limitations, it just was not feasible. Therefore, in addition to that, we also had to find a different way to go about this, to find an in vitro method to study the effects of microgravity on calcite crystals.
Next, let's take a look at our experimental procedure. First, it's important to mention that the Type 3 mini lab was used. We figured that this would be best for a double diffusion technique. This technique was adapted based on an experiment conducted by Shi Huang and his colleagues. In the chamber, the aqueous sodium carbonate and aqueous calcium chloride react to form calcite crystals within the gelatin matrix. The reason why we grew these crystals in the gelatin matrix is because otoconia, which we are basing this experiment off of, is formed in a gelatin matrix within the vestibular system. Lastly, it's important to mention that trials will be conducted both on Earth as well as the ISS.
Yes, and once both of these experiments conclude, we will use two primary techniques known as light and electron microscopy. For our experiment, the light microscopy will be allowed to help us count the number of crystals, where electron microscopy will be able to help us measure the lengths, the widths, the heights, and the volumes of these crystals. In further addition to that, there will be several statistical analyses such as QQ plots, t-tests, and histograms in order to analyze our data and get further conclusions for ours, since the previous study we're basing this off of had qualitative data and not quantitative data. And not only will these findings be crucial for future exploration in microgravity, but this will help future studies for treatment of balance-related issues here on Earth.
And that leads into a wonderful segue into our significance. So why should we dedicate so much time to an investigation such as this? Well, in all mammals, there exists a reflex that is called ocular counterrolling. This is where the otoconia within the vestibular system react in response to microgravity. This has been documented in space. For instance, in a study conducted by the National Institute of Health, astronauts in short-term spaceflight experienced neurovestibular dysfunction. They experienced symptoms such as dizziness, vertigo, and the inability to balance. If you or someone you loved has ever had a concussion, the same thing applies. When one experiences blunt head trauma, their otoconia can become dislodged, causing a bunch of unwanted symptoms. That's why this research is so important. By uncovering the mysteries behind our otoconia, we can help contribute to research by aiding those in space exploration while also being able to treat injuries on Earth.
And finally, we we would just like to acknowledge everyone up on the screen, everyone who could attend with us, everyone who isn't here with us, especially our professors that helped us back at our college, also our families, and the SSEP program itself, and everyone being able to attend and be here to listen to our research. It is a pleasure to share with you all. Does anybody have any questions?
Any questions for this team? Okay, thanks. Oh, got one.
Thank you so much. I really enjoyed your presentation. I find stuff about sensory really cool. So I was just wondering, how similar is the gel in your FME lab to the gel within the vestibular system? Maybe like density or composition?
So while I don't have an exact answer on that, we're actually growing our calcite crystals in a pigskin gelatin matrix. So I can tell you that there are some organic similarities between the gelatin within the inner ear and the vestibular system and the pigskin gelatin. So obviously, you know, it's difficult to be able to abstract the gelatin within our vestibular system, so we figured that we would switch to an organic-based compound to grow our crystals in to best mimic the environment that Otoconia exists in.
Thank you.
Any other questions? All right. Oh, another one.
Thank you. For the calcite crystals, what are you using some sort of crystal seed, or are you what are you using as the nucleus for the crystal growth?
That's a really good question. So what we're doing is we're reacting aqueous sodium carbonate and aqueous, let me check my notes real quick. Sodium carbonate and aqueous calcium chloride.
Okay, so it is reaction based.
Yeah, it's a
Okay,
reaction-based experiment, as well as there is a salt created in our experiment, as well as the calcite crystals, but that will be washed off and centrifuged as it is aqueous, so that'll be able to get us a better look at the calcite crystals.